Migrating a course to an AI platform is a transition from simple file storage to rigorous data architecture. Traditional folders fail because they lack the hierarchical context an AI needs to distinguish between a primary lecture and a minor reference sheet. To solve this, we replace the disorganized file pile with a structured course tree architecture. This tree structure grounds the AI coprofessor by defining the exact relationship between every concept and material in the curriculum. We can see this architecture in practice through Professor Haddad's fluid mechanics course, MECH 240. Haddad is teaching the behavior of physical fluids under pressure. Translating that physical reality into a digital environment requires a deliberate structuring of every lesson node, which serves as the briefing mechanism for the course's autonomous AI tutor. Haddad begins with a single lesson node, pressure and its measurement. He organizes his materials into 3 distinct buckets. The first is main content, which holds the primary material the student is expected to open first. Within the node container, the primary lecture PDF and video occupy the main bucket. The second bucket is for supplements, supporting materials like handouts, old exams, or reference links. For this lesson, Haddad includes a YouTube video of a mercury barometer demonstration he has used in class for years. After attaching these files, he previews every item for 30 seconds. This habit catches draft version slide decks or broken links before they reach the students. The third bucket contains the metadata, the lesson summaries, and learning objectives. This metadata provides the behavioral instructions that dictate how the AI tutor will explain these specific concepts. Together, these 3 buckets form the node anatomy. Respecting this anatomy ensures the lesson is a curated environment that the AI can interpret accurately. Haddad's lesson on fluid properties relies on industry standards that are subject to frequent updates. Specifically, the industry data tables for fluid viscosity were revised this past spring. This perfectly illustrates the currency problem, the time lag between the publication of new data and the traditional academic cycle used to update a syllabus. Haddad extracts the current text from the standards body's website and injects it directly into the lesson node. The Import from URL tool acts as a currency valve, allowing the course to stay current without a manual overhaul of the primary files. While the integration is automatic, the professor must still verify the accuracy of the imported text. On the trust ladder, a web page is simply another source, and the human remains the final verifier. This valve ensures the AI tutor teaches from the latest industry standards, even if the primary textbook is years behind. Haddad has one empty node in his tree, reading manometers in the lab. To fill this, he applies a specific division of labor between external and internal AI models. External workshop models are used to build the flagship materials, the slide decks and handouts that define the course's identity. In platform generation is used for scaffolding, filling gaps, and completing the course architecture. Haddad uses the Generate Lesson Notes function to draft the initial lecture notes for his manometer lesson. This internal generator uses the course context, attached references, and his specific teaching persona to ensure the draft fits the existing curriculum. This strategy allows the professor to focus his energy on core materials, while the platform automates the connective tissue of the course. After the system generates the notes for the manometer lesson, Haddad reviews the output. He evaluates the PDF against the same standards used for his own materials: logical sequence, consistent voice, and verified claims. The sequence matches his logic, and the persona-driven voice sounds like his classroom. However, he finds a hallucinated figure. The AI assumed a manometer fluid density that does not match his physical lab equipment. Specifically, the draft used a standard oil density, but Haddad's lab uses a water glycol mixture. He does not rewrite the text by hand. Instead, he uses conversational iteration. He provides a prompt with specific constraints: replace the fluid, use water glycol, and set the density to 1,050 kilograms per cubic meter. The platform generates a revised proposal that correctly incorporates these laboratory-specific facts. Detailed instructions yield a significantly more accurate second draft than a vague request for a correction. Because AI grounding shapes pedagogical fit rather than absolute truth, human verification remains the final, non-negotiable step in course assembly. With every lesson populated and verified, Professor Haddad looks at the completed MECH 240 module. The individual nodes, files, and links have been integrated into a cohesive unit. By defining the node anatomy, he created an environment where the AI understands which content is primary and which is secondary. By utilizing the currency valve, he ensured his materials reflect the latest industry standards, and through conversational iteration, he synchronized the generated notes with his actual laboratory equipment. This structural data is now ready for the compile step, where the curriculum compresses into an active model. This step brings the student's AI tutor online, grounded in the specific parameters of the course. By establishing these structural nodes and verified datasets, Haddad has provided the exact boundaries required for the AI to teach accurately as a representative of his course.